Now we will talk about least squares method. So we'll get into another Criterion, a slightly different approach from the perceptron, but still based on linear discriminants. So, you know, in regression, there is a stronger feedback on the nature of errors, you know. So if we are looking at what kind of targets we want, we don't want a binary values of 0 or 1. We are looking at in regression to approximate the real value of RT, which is anything in the space of reals. And as such, we are looking at the difference between the h of x and the r associated to that x. And these differences are really taken into account when optimizing our regression model. So somehow the target values RT in regression are more general than the discrete target values we are using in the classification. For example, for linear regression, we have this quadratic error criterion here, and which is the classical approach, is kind of the widely used criterion for regression. And what we are looking here, we are looking at the difference between the h of x versus the RT. And this is squared. So we are looking at the square of the difference, which is invariant to the sign of the difference. And this over all samples, contrary to the perceptron, which was dealing with the set of misclassified samples. Here with the linear regression, the quadratic error is looking at all the difference for all the samples that we have. So one idea is to look at how can we make the regression for classification. Can we apply the same criterion, knowing that the target values for classification are, I would say, simpler than regression? So regression is more general than classification. Can we somehow just take the approach, the usual approach for linear regression for making linear discriminants classification with a linear model? And as such, we will treat the targets, the -1, 1 targets, as real numbers that we try to approximate. So how can we do this? Is basically to start from the least square criterion, quadratic error criterion here that we have defined here that way. And this, we will just, from this, we will directly compute, evaluate the partial derivative for wi. So starting from this, we get that thing. How can we get that? Is simply to say, okay, something squared is like -2x it, because we care about factor wi. We don't care about the other x's. And we keep the element which is part of that RT minus h of t. For the developments, I think that's relatively basic calculus stuff that you can do on your own to prove to yourself. So this is this for wi, and for w0 it's similar, except that we are only having here -2, not -2x it, as we are dealing with the constant w0 here. If we set some kind of function e, which is the error we have for the sample xt, so that error is the difference between the target RT and the value we obtained from h, and we are computing the difference that gives us the error e of xt. And this error corresponds somehow to that part and that part from the two partial derivatives. And going into developing the delta applying to wi with that criterion, it gets us with minus eta partial derivative. So it's eta because we have a minus sign here that is simplified. So it is equal to eta summation over all samples of the function of error e of xt times xit, so the I component of the vector xt. Likewise, for w0, we have eta here. The minus sign is cancelled by that thing. Also, the 2 is cancelled also by that way, which was the same for the previous equation. And we are summing over all samples the error directly that we observe between the target and the h of xt. So directly, we've got a new algorithm, which is the least square classification algorithm, which is looking at somehow getting the output H close to the target RT. And the algorithm is similar to the perceptron. We start by initializing the weights to something arbitrary. Basically, setting this to 0 is doing a good job. So we have Wj equal to 0 for all the variables from 0 to D. And then we are iteratively applying modifications to the W's values according to the gradient descent. So this can be formulated that way. We are first computing the error, which is what the difference between the target and the h of x that we obtain. And from that difference, we are computing an update for Wj from 1 to D, which is that thing. So eta summation for all samples, the error times the xjt. And likewise for W0, we are computing the sum of the errors because we don't have any relations for the specific variable j, but we are using the summation of the error for all the samples of our data set and using this for gradient descent. So going back to the same example that we had with the perceptron, we are starting with the linearly separable case. So 6 samples, 3 blue crosses, 3 blue stars, 3 red crosses. So red crosses here, blue stars there. And now we are applying the least squares case for classification. At step 1, we have this kind of classification. We are still making 2. We still have 2 samples that are misclassified. And the error here, it's really the least square error that we've got on that. Then at iteration 2, again, we have a better placement. And here you can see after 2 iterations, this placement is correct. We have, in terms of classification, an error of 0. Everything is properly classified. But I would say in terms of least square, it is not perfect. Again, we have some kind of value here which represent the least square error on that, because even though these samples are well classified, they may not get exactly to the same value than RT. Said otherwise, the h of x has the good sign. If the RT is positive, the h of x is positive also, but the value is not exactly +1. It can be something smaller or bigger than +1. And as such, it gave us some kind of errors between the target RT, which is 1, and the value of h, which is different from 1. And same thing for the other class. The target is RT is equal to -1. So hxt is not exactly -1. It is something that can be bigger or lower, but still it is always negative, which is the right thing, which is making the right classification for that sample. And you can see after some iteration, the hyperplane is moving on. So we have some adjustment of that hyperplane. So we can see that this adjustment here is required in order to reduce, and the root mean square is reducing, is going lower and lower as we move this along. And this gives us to an interesting placement with relatively, I would say, better performance than with the perceptron, because the perceptron can be really poor. Here, I would say in terms of generalization, because the placement can be quite arbitrary. Here, at least it is making some kind of placement that is based on something that makes some sense. So again, like with the perceptron, the least square method will converge to some kind of configuration with linearly separable data. It will position the hyperplane to minimize the quadratic error. And it is putting emphasis on the data with the largest error. And that is important to be understood, because that means that there is a strong influence from well-classified data that are far away from the hyperplane. So even though we have a data that is properly classified, says that we are on the positive side, RT is +1 for a given sample, we've got an h of xt corresponding to that. That is right in terms of being positive, but that is far away. It says like h of xt is 6, for example. 6 is kind of much bigger than 1, and so the least square of 1 to 6 is 5, square 5 is 25. So it will mean that it will count for an error of 25, which can be quite important in the error criterion. And as such, the least square method aims at minimizing that error, even though, you know, the h of x is far away. So the x is kind of far away in the space from the hyperplane. So it is well classified, even I would say in the region that is remote from the decision frontier, which is perfectly fine, but is counting for a lot in the least square criterion. On non-linearly separable data, the least square approach is making some kind of good work. I mean, at least it tries to find the best possible placement of the hyperplane over the quadratic error. It tries really to deal with that as much as possible. So going back to our example with 4 samples that are non-linearly separable, so it means that there exists no separating line, separating hyperplane here that will give us a 0 classification error. And we apply the least square approach. At first, we have that value, which is basically 2 misclassified samples, 2 well classified. And over time, you know, it converges to such configuration, which is far from being ideal, because, you know, the best case we can do with a linear separator here is to misclassify 1 sample and get the 3 others right. While here, you know, we have a 50%. So the performance is kind of poor, because we can make many random placements that will achieve also 50% of error in the classification. But one thing to look at is that, you know, why are these 2 samples misclassified, and why are these two others well classified? And we can see that these 2 on the right are far away from the decision hyperplane. And so that means that they are also contributing a lot to the error. And so it's better here to get them well classified in terms of least square errors. And the 2 on the left, which are closer, have a lower impact on the least square error value. So this gets us to such kind of stable configuration for least square, even though in terms of doing well classification, it is far from ideal. So one other thing we need to look at is also the learning rate. I mean, this is the magnitude of the updates that we are making at each step of the gradient descent. So, you know, we have 3 cases here. So we have a first case on the right, which is the case here, where the step is relatively small. So that means that, yeah, it's relatively safe and smooth, but we make a lot of many iterations to reach some kind of global optimum here. So because the step, especially in the region that is kind of flat here, so this is relatively flat. That means that the gradient will be relatively small, and as such, the steps will be kind of tiny. On the right side here, we see another extreme case where the learning rate is too big. So here we kind of overshoot all the time. You know, we start from that position, we go really far away, and being here is in fact worse than where we were before. The position gave us a higher error. And continuing like this, we will kind of diverge. We will just move out of the space, and it will just kind of being far away as it goes, because the step is big. And so with a big step size times a big gradient, we are moving away from that space. So we need to be cautious. So the in-middle situation here appears the best among these 3, because, yeah, we have a relatively big step size that allow us to converge fast. Yes, we are overshooting here. I mean, it's kind of safer here to maybe stop before than going after, but still, you know, we are still reducing the error at each step. So we go from that place to that place in 1 step. The error has been reduced, and I would even say that it has been reduced, possibly not as equally, but not far from what we've got here compared to that thing here. But along the way, we are continuing to converge relatively fast by this overshooting again, but then we know it's kind of stabilizing and it is able to reach the minimum here in much less steps than what we have here, where we need many, many small steps to reach the minimum in that flat region. And as such, the learning rate has a big impact on gradient descent, and there are not necessarily clear rules to set it. Yes, we can have some ballpark values. There are some kind of rule of thumbs that have been proposed, but some good tuning on the data set or the kind of cross validation can get us with a nice learning rate that will allow us to converge faster than using some kind of arbitrary values that may not necessarily be adapted to what kind of data set we are dealing with and how gradient descent behave with that model.